I think we could be there. We could be live. And welcome to another build along. Another bit of Eurorack DIY. Can you believe it? Yeah, I'm going to be doing one of these very regularly now as Erica Synths release their educational range of DIY modules. The plan is to get together and to do them live right here on this mat, right in front of you, with no prep. Nothing but a box to open and some instructions to follow and to see where we get to. Yeah, more or less that's the plan. I've done a little bit of prep, but not so much as to put me in a position where I know what the heck is going on. The idea, the concept behind this is to get into the materials, to try to spend this time together to understand what this module is about, because these modules were designed to educate as well as to thrill you with the idea of building a modular synthesizer. They also hope to explain how these things are designed, how you put them together, and to actually do that on things like a breadboard before we then solder it together and turn it into a module. Now here's the one from last time. I've got it just plugged into a little fella here. Look at that. Sorry, just checking them online. The VCO, fantastic. We spent hours on that. Yes, we did. Hours and hours. But it was good, and we learned a lot. Now, I can't hand on heart say to you that I have absorbed all of the information that we gathered in the building of that, but hopefully some of it is still knocking around in my head, because that's going to help us. Because we're now moving forward into a VCA. And to some degree that's a lot simpler, but also it's very much a fundamental of Eurorack. And so in looking through the materials, I think we're going to spend about 30 pages working our way through what the heck this does. So that's going to be great. That's the plan for this evening. I'm not going to chat too much if I can help it, because the one thing we learned from the VCO build is that it can take a long time. Particularly if you hit snags and things you don't quite understand, you need to keep working through them and work them out. That really did take some time. So the plan I've got sketched out is for the next couple of hours to work through the explanation of what a VCA does and how the design works in the manual, and to build it on the breadboard as directed, and to get that far. I think it's unlikely we'll get to the soldering stage. It's possible. I mean, if we get through all this in an hour, then whoa, we'll just go for it. But I imagine we'll be doing the soldering on another night, and I'm planning at the moment for that to be tomorrow night. We'll just see how this goes. It may be that there's more that I need to do, in which case we might have to delay it till next week. But the plan will be to do the soldering of the kit tomorrow night in another live stream. Yeah, that's the plan. That's the plan. So what I would say also at the beginning is that a lot of the information we do, well, all of the documentation has been provided by Moritz Klein, and he has his own YouTube channel which goes into a lot more depth about every aspect of Eurorack modules, design and implementation, lots more breadboarding and explanations going on over there. So that should be used as a companion. Just Google it. If I haven't linked it in the description, I think I might have done, but it's Moritz Klein, and it's in the manual, which you can get from the Erica Synths website. Just look for the EDU DIY VCA, and if you go to the shop page for that, you will find the manual listed there, and you can read along with us. So a lot of today, unlike last time was a lot of breadboarding, a lot of stages on here going along towards building the VCO and understanding the different parts as we went. This time we're really only talking about one thing. We're talking about volume control and using voltage to control volume, to control an amplifier, which is what a VCA is. And so it's actually a much simpler thing, but there's a lot of explanation gone in, a lot of work gone in to how all that functions. Now, we're in the middle of a bit of a storm here where we are at the moment, so if it all goes dark and it's probably the power lines are down or the shed has collapsed. So, don't worry, and we'll try to work that out later on. So, good. So I'm going to shuffle myself into a better position, I think, and we'll get stuck into the manual. There's going to be a lot of reading, I think, this evening, but don't worry, we're just going to read along. I'm going to read it and try to not expand upon it exactly, but reason it out and think about it as we go. Do some breadboarding, do some building, see where we get to. That's the plan, all right? That's the plan. So are you doing all right out there? Hi Ken, hi Robin, hi Meebit. Good to see everybody. Corey, Scott, Jaden. Moritz, of course, was also in the house, which is a delight. And yeah, I would like to say, yeah, a massive thanks to Moritz, actually, because at the last one, the first one we did, it really was jumping in, you know, at the deep end, giving it a go. And it did reveal some, you know, what's the word? Some gaps, perhaps, in the manual and other bits and pieces. And he really has worked overtime to improve the original manual on the VCO and the further ones as well. So there's stuff in here that's come directly from all that fumbling about we did with the VCO, which is brilliant. So masses of respect to you, sir, in taking my criticisms and my stumbling on board and trying to make it easier for people. That's just awesome. That's totally brilliant. So there's something new and exciting in the manual, which we'll come to in a little bit, but I think we should probably just get on with it. So yes, so let me change my view to I forget which one I want. I want that. Do I want that one? Just 1 second. Smooth as silk is what that is. Smooth as silk. That one. A manual one, hasn't it? Number 5. Stand by. Nothing bad going on. I'm just dropping things, breaking things. Ugh. That's live telly for you, you see? Live telly. What did I say? It was number 5. Let's try that out. Why don't I go and look on this on somewhere so I can see what's going on? How do I do that, I think? Seamless, yes, I know. I'm just going to bring up... so that I can check on myself. Okay, there you go. You can see my Googling. Excellent. So where do I want to go back to? Here, there's the manual. Get rid of that. That should work. Good. Right. So I will skip through as much as humanly possible in order to save on time. So the introduction, I'm sure, is fabulous, and you can read that in your own time. So one of the things I'd like to point out, which is new in this version, since we did the VCO, is a bill of materials, which is very exciting because it was absent with the VCO, and it left me kind of floundering around, not being entirely confident as to which components I had, whether I had the right ones in the right order. Those sorts of things. And a bit of materials is just really useful, and the sort of thing you get, the sort of thing you have with anything that you're building, you know. So it seemed a bit weird in its absence. The thing, if you're going to be building along, what you will need is a breadboard, like so. You can get these from Amazon for £10. A bunch of patch wires, and these fellas. Probably a multimeter, some 9-volt batteries. These guys, with some clips to enable you to attach them to the breadboard. That's it. For more information on all that, do check out the first in the series. So let's not look at this quite yet. Let's just have a check on the manual to see where we go to start with. So the VCA is one of the fundamental building blocks of any modular synthesizer. No rack is complete without it. And he came up with a simple circuit for his own modular system. It's fairly basic. That's what we like. Basic. Basic is good, and yet super efficient. Made of just a couple of transistors and some op amps. Now here is a sketch of the circuit. This is it. So can you? I think you can see the mouse. Yes, probably. Transistors in the middle here, a pair of transistors, which we'll try to understand and work out at some point. Then an op amp over here, op amp over here. Simple. An in and an out. Well, no, there's a signal in and a CV in to control it, and an out over there. That's it. Not a lot. But now we have to work out, find out how it works. No, I haven't given up on the Descartes dream. It's right here. Look, right here, all the bits. Look, there's the power. There's the back of it, right there. It's all, it's all ready to go. Just got to find the time to finish it. I don't have any time. I need, you know, a generous benefactor. If I had one of those, then I could get on with all these bits that I'd like to. Anyway, I digress. Don't get distracted. Right, good. Yeah, get rid of the phone. Put that over there out of the way. So, yeah, and I mean, and actually, in reference to that, I'm not trying to teach you anything. That's not my role. I'm trying to learn stuff. I'm trying to learn how this VCA works. So I'm not sitting here going, I know how VCAs work. I'm really up on all this. I really don't. And so I am here to learn. That's what this is about. So what you are watching or sharing in is my learning experience, not me teaching you anything, because, well, for lots of reasons, because I want to learn, but also because I think this is interesting because when you're being taught something by a teacher, their experience of that material is always very different to yours. So they often, no matter how good the teacher is, can make assumptions about what you know and are trying to present decent information, and you're just, you know, trying your best to absorb it. But I think in coming together to attempt to learn something, I think we have more opportunity and more chance of really teasing out what this is all about. Anyway, I've wasted 15 minutes already. We need to get stuck into it. Right, so the bill of materials. So we're going to check through what we have, because we are going to need these at some point. We're not going to be doing any soldering just now, but we are going to be putting these into the breadboard. In which case, let me just swap to the overhead. Okay, and we will just have a check through all the components, because that seems like a positive start. It means I don't have to start reading quite yet. Box to one side. So let's just have a quick look at the PCB. So this is where we're going to get to. Let me know if the sound is all right in the chat as well, because I've moved the microphone about. If it's too loud or too wrong, do let me know, and I can change things. So here's the PCB. Nice. A lot of crowded stuff going on in here. That's interesting. Again, we have this array of patch points here, which can be used for sort of for your own modifications, which is not something I'm likely to do. So that's the PCB. Here's the front panel. Just very simple. 2 VCAs. 1, 2. That's it. Identical, as far as I know. Is that a hole there on purpose? What's that for? Don't know. There's a hole in the middle of mine. Is there supposed to be a hole, do you think? No. Yes. No. That's the VCO I'm looking at. Dun, 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 dun. Okay, very interesting. I seem to have a hole in mine. I imagine that's only cosmetic. Not gonna feel funny about it. Interesting. Not supposed to be there. Hang on a sec. Hang on. Stay there. No, I was just checking because Erica did send me a couple of sort of some duplicates of one or two of the modules, but not the VCA. So we're not going to worry about that hole. That's not going. We're not going to draw any more attention to it. I'm going to put that away over there. Okay, we've got a bag of patch sockets, a couple of knobs. Those are going to come in useful very soon as the power adapter. Just going to keep them in their bag for the minute because we're going to focus on these bits here, just in order to get them identified. Okay, so resistors. Transistor-y kind of things. More resistors. Some diodes, more resistors, and some of those. Right, good. Where's my pen? Super. So we were on a bit of materials. So this allows us to check that we have the things we're supposed to have. So there should be 12 100k resistors. Now I think these are 100k because there's a batch of 8 of them. And according to the bit of materials, there isn't 8 of anything else. And look, there's another bunch of 4. Is that the same? No. Hang on then. Are those the same? Alright, I'm going to have to do a little bit of investigation then. So there's supposed to be 12. But those are definitely 100k, I think. Now, I'm going to have to get me meter out. That's the only way I'm going to get this done. If you don't have a meter, obviously you can go and check what the bands are and go and check those on. If you just put in resistor bands into Google, it will tell you, it will find you a website. There's plenty of different ones. Some really useful ones as well, ones that like, I don't know what would be useful about it. I don't know. You stick in the colours and it tells you exactly what it is. Right, so those are 100k, absolutely 100k. Get off. So I will go through the rest and see if we can work out what they are. So those are 100k, these ones. There are 4 of these that I can see. So these are likely to be hundreds, although there's others that are in 4s as well, and 6s. All right, make no assumptions. That's the best thing at this point. $10k. There should be 6 of those. So that's 10k. So there should be 2 more that look exactly the same. I'm going to have to stick my magnifiers on already. It's crazy. I cannot see. So we have got purple, red, black, black. Can I find some more purple, red, black, blacks? No, I cannot. That's not far off. Right, well, we're just going to keep going with it. So that's be 10k. I should have 6 of those. But let's see what else we've got first. Okay, these 4 are 100k. See, that's interesting if you're new to this, just to look at these, that these are both 100k. Yeah. Now, they look very different. It's only because they're slightly different makes of resistors, or they've come from a different batch, which means they're a different colour. But I think if you look at the bands, you'll find they are actually identical. I'm just going to look at them. Look at them a little bit closer myself. Yeah, well, to some degree. So if you can correct me if I'm wrong in the comments, of course, but I think that brown is 1 and black is 0. So I've got brown, black, black on both of them, and then orange, which will be the 1000 to make it 100k, and then the last ring, which here looks kind of purpley and on this one looks a bit more brown, is kind of the tolerance. So it's kind of how really good they are, how close they are to the actual value they're supposed to be. They're all going to be within tolerance, it's just that they're slightly different. It may well be that that's supposed to be the same colour and I just can't see it. I don't know. But suffice to say, I've measured it and these are both 100k and the bands are more or less the same. It's so precise, this here business, that we're going to go with that. So those are 100k. Okay, good. Right, keep going, full. Keep going. Don't slow up. What have we got here? I'll have a look in the comments in a minute. 20k. Supposed to have 6 of those, so that's the first 4 of 20k. See, I did think about measuring and naming the resistors before I came on air, but then we would have missed all of this fun, wouldn't we? Somebody suggesting I should read the chat. Okay. No, anyway, just going for it. So that's 20k. So yeah, just regards to the hole, as somebody mentioned they didn't get one on theirs. I got my set of modules ahead of time. So they've probably worked that out now. If there have been any weird problems. Similarly with the actual resistors and stuff in the kit, it may well be that you get slightly different looking stuff now that they're putting together a large amount of them as opposed to a few kits for special people like myself. So do be aware that things can look slightly differently. These ones, 10k. Again, there's supposed to be 6 of those, and so there's 2 which are 10k, which makes those other, goes to those other ones. So suffice to say that your resistors don't always look exactly the same, even if they're supposed to be the same value, and that's okay. Check the rings, check the colours, or measure them with a multimeter, and you'll know. 1k times 2, yeah, okay. Those are 1k. $20k. Six of those. See, just the fact that I have a bill of materials which tells me how many of each I've got means I'm completely confident about this, even though there's different colours going on, different types of or make of resistor. I'm not worried about that because I know how many of each they're supposed to be. There's no guessing involved. 82k, 2 of those, yeah, cool. 82. Ooh, the shed's a bit shaky. 100 ohm. I'm not the least bit worried. There's only 4 of those. These last two, 10 ohm times 2, 10, yeah. 10 ohm. Great, so that's all the resistors present and correct. Try to place those to one side in some kind of ordered fashion. Good, because I'm going to need those. Next up, a few capacitors, it suggests. We've got the rolly ones here, the electrolytics. These should be 47 microfarad, which they are, written on the side. Those are easy. These little sluggy ones should be 100 nanofarads. Ceramics, 104, just got written on it. There should be 6 of those. 1, 2, 3, 4, 5, 6. Yep, cool. Diodes, 2 of those. Scotch key. Big fat ones. Good. Couple of transistors. Should be 4 BC548s. BC548s. Yeah, because if you remember from the circuit diagram, we're going to be using 2, but because this is a dual VCA, we're doing 2 whole lots of it, so we'll need 4. That's them. This is easy this time around. Pair of trimmers, fantastic. A few pots, yeah, got those sockets, yeah, in that bag. A couple of chips, TL072s. TL072s. That's got the op amps on. So all present and correct. Good. Good, good, good. So with that understood, we're going to go back to the manual and spend some time learning about volume control. Sadly, Ken, I can't start on the beer because I won't finish. I've got beers in the fridge. I've got some ghost ship waiting for me when I've done this, which I'm much looking forward to. Right, let's go. So, volume control basics. So, I mean, I'm not trying to do anything clever here. We're just going to read through the materials as best we can, and try not to get too bogged down. Now, this goes on till page 30. We're on page 5, so there's quite a bit of stuff here to try to absorb. Let's just do our best. See how we just see how it rolls. Yeah. So let's answer the most essential question, which is, what does a VCA do? Well, I think we pretty much know at this point. Obviously, please read this manual in full many times. You'll also find things about individual components, information about individual components at the other end of the manual, sort of in an appendix if you want deeper information. So I'm going to gloss over some things which you can spend more time on, both in Moritz's videos and at the end of this manual. So do be aware of all that. There's great stuff in here that you shouldn't be glossing over, but we're not going to hang on every single word. Does that make sense? Just going to see how this goes. So the simplest way to think about it is a volume knob where you turn it to the left and it goes down, turn it to the right and it goes up. But a volume knob by itself is not automatable. You can only turn it by hand. But in modular, we want to be able to control it with LFOs, with envelopes, with sequencers. So we want it to be voltage controlled. So what we're looking for is basically just a volume knob that can be controlled with a voltage. Yes, and that's what a VCA is, voltage controlled amplifier. It's where a low level voltage corresponds to a quiet, while a high level voltage gives us a loud output sound. So if we control our VCA with an envelope, for example, it gives us a volume curve. We know that. So in order to design a VCA, we need to take a step back and talk about basic boring volume knobs again and how they work. At the most basic, they are just potentiometers set up to be variable voltage dividers. Now, we did voltage dividers in the VCO. So we know all about that, right? Yeah, well, kind of, but let's keep going. So it suggests we can find out more about potentiometers in the end of the book, but we're just going to keep on sticking from where we are at the moment. So in electronics, sound is just a swinging voltage, and the bigger the swing, the louder the sound. I think that's a really interesting way of looking at it. Sound is a swinging voltage. Yeah, I think that's brilliant. The bigger the swing, the louder the sound. Voltage dividers do just what their name implies. They divide or scale down any voltage you throw at them. So if we set our pot to precisely 12, this means that two resistances inside the device are exactly equal, giving us a perfect 50% voltage divider. That slashes our sound's volume in half. Turning it to the left will reduce it, turn it to the right will amplify it. Why? Because we're changing the relation between the two resistances that make up our voltage divider. And it's that difference in resistance that changes the sound. So we're going to use the water analogy. Looking a little bit closer at the voltage divider. So if we think of electricity as water flowing through a system of pipes, with voltage being pressure and current being the flow amount per second. Voltage is pressure. Good. Then resistors would be narrowings in the pipes. You can see that in the picture on the screen. It looks a bit like a Christmas cracker. So you've got the pressure being the voltage, the flow being the current, and the narrowing being the resistor, which restricts the flow. Yeah? Okay. So we imagine we apply a steady amount of pressure to the top. Since our system is wide open at the bottom, we'll see water flowing downwards. How much? That directly depends on how narrow the pipes get. This is quite literally the bottleneck in this scenario. To make our lives a little easier, let's quantify things. We'll say that both our narrowings are exactly equal in diameter, 1 centimetre say. Individually, they'd let the same amount of water pass through in this setup. Two restrictions. Yes, okay, I'm with you. 10 millilitres per second, apparently. But placed in series, that amount would be slashed in half, giving us a flow of just 5 millilitres per second. What? Individually. Okay, sorry, okay. Individually, a 1 centimetre narrowing individually on its own, so not like in the picture, which is 2 in series. Individually, they restrict it to 10 millilitres per second. But if you place them in series, one after another, they would be slashed in half, giving us a flow of 5 millilitres per second. So it's fair to say that there's some unused potential here. The two narrowings are basically handicapping each other. Okay. I like to think of it like this. If we were to bypass the second narrowing, so just go straight out of the side, we'd suddenly see a flow of 10 millilitres. This is simply because we got rid of the additional bottleneck. Now the question is, where does the unused potential go when there's no bypass? The answer is simple, it doesn't go anywhere. It just stays in the middle between our two narrowings as pressure. How much pressure? Well, since the full realised potential is a flow of 10 millilitres, we'll see just half of that. The remaining pressure is exactly half the pressure we apply at the top. Yeah. Okay. So we've got pressure of water at the top, and we've narrowed it so that the water flows through it slowly. If the pressure at the top is maintained, then if it was a straight-sided glass, the pressure would be the same all the way down. But because of the narrowing, it's restricting the flow, so it's restricting how much water can get through at one time. And we're saying that that restricts it by half. So if in the top it's, restricts it, the pressure by half. So Individually, they'd let the same amount of water pass through in this setup, 10 millilitres per second. Individually, they would, yes. Gotcha. But if you put them in series, it ends up being 5 millilitres per second. Okay. So knowing this, we can derive what happens when we change relation between these two narrowings. If we make the bottom one wider, we'll see two things happen. First, the total amount of flow will increase. Second, the amount of pressure in the middle will decrease. So the voltage in the middle will go down, but the current will increase. This is because we partly de-handicap the upper narrowing, which allows for more potential to be used and converted into flow. On the flip side, if we make the bottom narrowing tighter than the other side, the flow will decrease and pressure in the middle will increase. An important thing to keep in mind is that when we're focusing on pressure levels, the absolute quantity of flow does not matter at all. The amount of water doesn't matter. It really is only about the relations and proportions, about the relationship between those two narrowings, those two resistors, and about the voltages going through it, which is the amount of pressure. So regardless of whether we have a total flow of 5 millilitres or 5 litres, as long as this is half of what could potentially flow with just one narrowing, we effectively halve the applied pressure. So these are two identical narrowings, and that's the point at the moment. That's where the halving is coming in. Okay, but so far we've assumed the pressure at the top to be constant. Yes, an audio signal is a swinging voltage, meaning it will change over time. This would mean that our pressure is getting more or less intense, and sometimes even going negative, essentially turning into suction. Ooh, crikey. Now obviously a voltage divider works with audio signals, so it can handle big, small, negative voltages just fine, always dividing them by the same factor. But why is that? Because resistors have two properties that make this possible. Linearity, oh my goodness. Linearity, linear, IT, and symmetry. Linearity, oh God, in this context, I am sorry, it's just, my brain sometimes just doesn't do it. Oh, well, Nicholas, that's just lovely, and so you should. That's an awesome name. She's going to be awesome for her entire life. Click the link in the footnote. I haven't got to the foot. Oh, yes, I have got. Have I got to the footnote? Yeah, no, yes, absolutely, yes, going to get to that. Okay, I'll see that in a minute. I'm just going to finish this paragraph. Where was I? Yeah, linearity and symmetry. Linearity in this context means that there's a linear relationship between the voltage applied to a resistor and the current that will flow through it. So a doubling in voltage will always result in a doubling of current. Okay, this is all good, but there was this thing that I mentioned earlier, which is there's a new feature within the manual, which is this awesome circuit simulator. Now I've had a quick look at these, and I can't tell you exactly that it's going to instantly improve everything, but it's quite extraordinary what we're looking at. Oh, I didn't look at this one, I have to say. Oh, right, so this is interesting. I hope you can see that all right where you are. I'm not covering up by some strange factor. No, it looks good. Right, so these I can completely destroy. I can pick them up and I can move stuff about so it no longer functions. Like, isn't that brilliant? Let's not do that. So we have, can I pinch zoom? No, I can just make it really, really small. Damn it. That's brilliant. 1 second. Oh, poo. Let me open it again. Okay, that's good. I'm not going to try to zoom in this time. Oh, look, there's things at the top. Maybe that's it. Anyway, it doesn't matter. That's not important. So if we look at this baseline divider one, this first one here, this is when he talked about having this bypass. Sort of. So if we're talking about flow, which is current, pressure, which is voltage, got a plus 10 voltage pressure at the top with these two resistors that are equal to this flow, two 1K resistors, we get 5 milliamps in the middle. That's the flow, and you can see the speed that it's flowing at because of the two restrictions. Now if you add a bypass, so you bypass that straight to ground, it flows faster through there because it's only got one restriction and comes out at 10 milliamps. So it's a halving or a doubling. Do you see that? So if you double that input, it's now got 10 milliamps in the middle, pressure of 20 volts, 1K resistor. I confess I don't know what this middle thing about 5 volts and 10 volts here, which appears to be half of the 20 volts. Is that important? I suppose it is. But what is that doing? Is that a measurement at that point? Measuring the voltage, or is that an output? Even though the flow doesn't seem to be going to this output. Does that make sense? Oh, God. It's the confusion trying to wrestle with resistance, voltage, and current. It's a conundrum. I mean, it's science and all that, but trying to get those concepts fluid in your head, I find quite difficult. I can understand them in their own situation. It's difficult really understanding the relationship fully, I find. Mouse wheel? Could have been. Could have been. So I've doubled the input, so it's 20 volts, which gives us 10 milliamps, because V equals IR, voltage equals resistance times current. Come on, get a grip now. And with the bypass, so essentially it's just saying if you double the input, the pressure and the flow is also doubled. That's all it's saying. So if you do the bypass, you get the 20 milliamps straight out because you're just going through one. If you go through both and you've got both going on, you get 10 milliamps through. Got it, okay. There's a negative input. Now, when you talk about audio, because it's going to be going up and down in terms of being a wave file, a sine wave, spinning around the point of zero, you're going to have negative as well. So that's essentially going exactly the same way. It's just that you've now got a negative voltage, but you've still got the same current going through. And again, if that's quite strange when you put the bypass in, because one imagines that current is flowing from one thing to another. It's flowing to ground, whereas in this instance, it's flowing out of ground at 10 milliamps and back up that way. It's weird, this electronics business. I would like to point out that Moritz's commentary is going to be invaluable to you while you're working your way through this. So do have the comments on. And if you can't see them, then you need to go to, if you're watching this on Twitch or you're watching this on Facebook, then head over to the YouTube channel where all the live comments will be there. Yeah? Okay, so variable static input. Am I allowed to move that? Is that going to be bad? Adjust me via sidebar. What? Oh, what, over here? This one. Current circuit. Knob 1, knob 2. Oh no, that's that one. Oh, that's weird. This one. Yes, look at that. Okay, so in this variable, so assuming you've got a static input, if we move that resistance, the point between these two things, which is changing the resistance on either side. So we've got a pot, okay, variable resistor type potentiometer, which is a voltage divider which is changing the resistance on either side of itself. That's going to change the output voltage. You can see that as you move up and down. Now the link to this page, in case you're wondering, is in the manual. It's in the footnotes on the manual. And this is invaluable. Okay. Now the last one here is variable audio input. You see that? It's a little bit off the screen. Which again I can move through this panel on the right. And this has got a WAV file coming in, a variable input. So the amps are changing all the time, the flow's changing all the time because the input is changing. So but if we change that knob, we can see that the size of the output changes. So to big, down to small. Now there's a slight flaw in the metering, that it seems to kind of average itself out, so it then goes big again. But you can see as I move it, that's what's happening. It's getting bigger, it's getting smaller. Amplification, attenuation, that's what we're after. Good, right, back to the old manual. Now we may have now gone past a few bits, but let's just keep going. So we got to the point where we have these two properties of linearity, yeah, that's better, that's how you say it. It doesn't read the same, does it? Linearity and symmetry. So if we double the pressure, we get double the amount of water flowing through our narrowing. Since this is true not only for multiple narrowings in series, but also for each individual one in isolation, our potential actual flow model still works out the same way. So for a doubling in pressure, we get a total flow of 10 millilitres instead of 5. Add a bypass and we see a whopping 20 mil flow through. Okay, since 10 mil total, still half of these 20 mil that could potentially flow. But what about negative voltages? Yeah, this is where the symmetry comes in. For resistors, the direction of flow doesn't matter. The restrictive effect will be the same in either direction. So if the pressure up top goes negative, we simply add a minus sign before all our values, indicating that the direction of the flow has been inverted. But since minus 5 millilitres is still half of minus 10 millilitres, everything works the same, and we get our half of the pressure in the middle. To try this in practice, here we go. Breadboard time. This is exciting. David, it's really nice for you to be on Facebook. I am still persevering with this restream business where I'm streaming out to Twitch, to Facebook and to YouTube, just kind of because I've paid the subscription, so I thought I might as well use it. But Facebook isn't being greatly utilised, I have to say, so I do appreciate you being there. I can see your comments, and you're very welcome to stay there or pop over to YouTube where you'll find far more people watching. Cool, right, so what are we looking at? Bit of breadboard practice. So I'll just read through this and then I'll swap the camera to this. So grab your breadboard, set up, very simple circuit shown below. It uses a 100k potentiometer configured as a variable voltage divider with an audio signal sent in via the right hand jack socket. You then connect a pair of headphones to the left socket. It's a passive circuit. Hooray! We don't need to use any power supply. Good, right, so let's go back to the overhead. See that all right? Not too much of that glare. Something about that glare. One of these days I've got to work out my lighting properly. So this is relatively simple, we like to think. We're going to need some patch sockets and a pot. pot. Why don't I just tip them out like a normal person? Okay, cool. So I've got a pot. The pot's got 3 lugs on it. We tend to, using the breadboard, going to bend them out. Zoom this in a little bit. I think it might be good. So that they stick in a bit more sensibly. Then you've got to decide whether you want to stick it that way or this way. Doesn't really matter. The numbers don't matter. We're just going to stick this into 3 lines on here. Like that. And it should just sit in. Cool. We then need 2 patch sockets. Now Moritz has done a good video all about breadboards, which would be worth your time if this is your first time looking at this. Put that in there. But basically the idea is these ones on the edge are connected this way. The ones here are connected this way. Obviously there's a big gap in the middle. And so you can use it as lines in order to connect components together. So if these 3 plugged in as demonstrated, I've got this little one that sticks out here, and that's the one that sticks out on the picture. So plug those in. Now none of that's connected to each other because all of the rows are running this way. This is how the connections goes. So to connect them up, we're going to need to use some patch wires, which is what these fellas are. Now if you were sensible, you would have got really small ones, but I wasn't sensible, so I ended up with these really long ones which get in the way. Don't worry about it, it's just as it is. So to connect this up, the back end of this patch socket I can connect there. That is going into this first pin on the pot. So 3rd one there goes in like so. The sticky out sort of earth leg here connects over to this bottom row here. The middle pin, so I'm going to go 1 up, let's use a different colour. Goes to the first pin on here. And lastly, this end here goes over to our sort of earth bit at the bottom. Now there's one more, which is the 3rd pin on the pot. Which is there, 1, 2, 3, also goes to our earth rail along here. Doesn't matter what this is labelled, it doesn't matter, as long as they're all on the same one, because this is connected all the way along here, and this is usually what holds our power. That should be it. So now we need to be able to hear something. So for that, oh, I unplugged it, that's a shame. There's a thing, there's a thing. So I'm going to use our VCO from last time to generate a sound. And I will plug now. Which side do we plug things in? So this is a 100k potentiometer configured as a variable voltage divider with an audio signal sent in via the right-hand socket. And then we need to hear it. So I'll need a slightly longer cable. Go. Long enough? Not quite. Not quite. I put a a long cable somewhere. Good. And then we're going to take the output, plug that into. I've got an output section here. lastly, I need to plug in some sound. In the tidiness that is my shed, I'm not planning on doing any soldering today, so the soldering iron is not on. I must keep reminding myself. Okay, plug that in there. Oh, in case you didn't see this earlier, right? I'd missed out a whole resistor on the VCO, like an idiot, which was essentially restricting the range of the coarse knob. Whereas now I put that one in, and you'll find the video on the YouTube channel, and it's now got a much greater range. So anyway, so this is going into our thing here, and if we turn this knob, I'm assuming we will hear a change in volume. Good Lord. Are you experiencing that? So there we go. So by turning the potentiometer, we should now be able to change the signal's volume. With this, we know why voltage dividers are a good fit rather for manual volume control. But the question is, how can we modify them to give us a voltage-based volume control? Well, if you watch some of my earlier videos, you might already be thinking of a certain direction here. No, I'm not, because I haven't. Well, you know, a little bit. I mean, I imagine that we're going to do something clever with transistors, which is what we did last time on the VCO. We started off talking about voltage dividers and pots and things, but we ended up using a transistor because of its exponentialness and also because we could temperature control it. Something like that. Anyway, so let's see where we go to next. Okay, some good extra information down here on this in the footnotes, just expanding a little bit in order to help you put things in properly, which is great. I'm really enjoying the additional information, I have to say. So this brings us to a whole nother section. I better bring that up on the screen. Cool. So resistors versus bipolar junction transistors. All right, yes, that's the fella. Oh, David, well done. Oh, you've left Facebook all lonely. Oh well, good to have you here. So this is Moritz speaking within the manual. In my DIY VCO series, I claimed that you can use an NPN transistors as voltage controlled resistors. Yes, he did. That's what he did. Absolutely, he did do that. And that's what we did. And if that was true, then something like this should work, right? Yes. We could simply replace one of the two resistors in our voltage divider with a transistor. Then, by applying a voltage to the base, we should be able to control the amount of resistance between collector and emitter. Voltage into the base controls what goes through between the collector, the input, and the emitter, which is the output, what goes in and out of a transistor. And that giving us a voltage-controlled voltage divider in total. Unfortunately, if you build and try this, you'll be severely disappointed. And that's because what I said in the VCO video, was at least misleading, if not flat out wrong. Good gracious. A bipolar junction transistor is not a voltage-controlled resistor. Alright, there is no resistance in that sense between its collector and emitter. Right. To understand this better, let's talk about what resistors and transistors have in common and what separates them. On the common side, both components allow us to restrict the amount of current flowing in a circuit. This is why superficially they seem kind of interchangeable. So here's an example, two circuits. One is just a resistor with a voltage source and ground, the other is a transistor with its collector connected to an identical voltage source. Its base connected to another much weaker voltage source, and its emitter connected to the ground. Now if we tune the base voltage carefully, we can get exactly the same amount of current flowing through our resistor and our transistor. Okay, This might lead you to believe that for this base voltage, the path between collector and emitter acts like a 20k resistor. But if it were true, then it would need to exhibit the same two properties that resistors do, linearity and symmetry. Let's check for linearity first. Doubling the voltage applied to the resistor gives us twice the amount of current. But for the transistor, something odd happens. Nothing happens. Doubling the voltage applied. So that's at the top. Voltage at the top being doubled. Nothing happens to the bleeding transistor because it's governed by what's coming into the base. Because the only thing determining the amount of current that can flow between collector and emitter is the amount of current flowing into the base. The base controls it. And the latter only depends on the voltage, and the latter only depends on the voltage at its base, not the voltage at the collector. Now, while this would already disqualify the transistor, let's also check for the symmetry, see what happens when the collector goes negative. So interestingly, our transistor would theoretically still work roughly in the same way. We'll see a current flow between emitter and collector, but it won't be the same current, just inverted. Instead, it will be a ridiculously strong current that will wreck our transistor. This is simply because the huge negative voltage between the base and collector pulls a too much large amount of current into the base, disqualifying the use case without further alterations to the circuit. So it's official, transistors are not voltage-controlled resistors. Okay, so within the VCO then, it must have been a particular use case. We were using something to vary the voltage at the base of that transistor. We were using it to keep the temperature control thing going on. That was the reason we were using it, if I remember rightly. Anyway, let's read on. Let's see what happens next. So this is the reason why the initial idea of the transistor-based voltage control divider does not work. Since the current going through our transistor is fixed, if the base voltage does not change and the collector voltage stays positive, the total current flowing will be fixed as well. So in minus inverting. So inverting or decreasing the collector voltage will only change the potential, not the actual flow amount. Okay. Okay, I'm just thinking. Right. Potential being voltage, yeah. This means that the ratio between potential and actual flow is not fixed anymore, and that's why this setup simply does not work as a voltage divider. Here's how this pans out in detail. Let's assume that we've set the base voltage so that our collector emitter current is exactly 300 microamps. Then the total current going through the transistor and the resistor is also 300 microamps. Since a 20k resistor could potentially allow for 600 microamps to flow, if we bypass the transistor, the ratio between potential and actual flow is exactly half. So we'd measure 6 volts between resistor and transistor. Okay. Now if we double the voltage at the top, the current flowing will stay the same, but the resistor could now potentially allow for a flow of 1.2 milliamps. Why 1.2? Ratio shifts. Okay. Now if we double the voltage up top to 24 volts, the current flowing will stay the same, 300 microamps. But since the resistor could now potentially allow for a flow of 1.2 milliamps, our ratio shifts from a half to a quarter, 4 times that, 1.2, 4 times. All right. Meaning that we get 3/4 the voltage at the transistor's collector. As we can see, the increased voltage simply gets added to the previous value, making this setup unsuitable. I don't really understand all of that, I'm afraid. But the point is that we can't use the transistor in this situation. We could previously, and I'd have to go back to the VCA documentation to understand why it was suitable then and not suitable now. But it says it isn't suitable because lots of stuff happens that I don't quite understand the relationships between. But this is what it's saying, and so that's fine. I'm going to take them at their word, and we should probably move on and use something else in that case. But have I got this? Not really, no. Not really, but I'm not going to dwell on it. It's something which we can work on and come back to and learn as we go. We're not going to grasp everything in one pass. So transistor amplification 101, this is what we're trying to get to. So if we can't use the transistors as voltage-controlled resistors, how can we use them? Well, one of the main applications is actually amplification. Transistors can take a very small voltage swing and scale it up massively. Well, that's useful, let's do that. One way to do this is by setting them up in what's known as the common emitter amplifier configuration. Footnote 11. You can try this in the simulator. Good, right, we'll get to that in just a second. At its most basic, it would look like this. So something coming in here. It's filling around with the base of the transistor. You've got your 20k, what's it here, which gives 600 microamps. You've got 7 to 1 volts coming out over there and stuff coming down here. Come on, come on, keep it together now. So we apply a very weak 20 millivolt peak-to-peak signal with a comparatively big, we apply a very weak little millivolts. Where does that millivolts here? Okay, a weak little 20 millivolt peak-to-peak signal with a comparatively big 570 millivolt offset. Right, so a small amount, but it's offset 570 millivolts to the transistor base while monitoring the voltage at the transistor's emitter. Right, and here we'll notice something strange. Compared to the oscillation we send to the base, there's a huge voltage swing at the collector that looks a lot like it over here. Just slightly distorted. What's up with that? To answer this, we'll have to understand the way the base voltage relates to the amount of current allowed to flow between our transistor's collector and emitter. Right, so let's have a look at this simulation. Okay. So we have this little input to the base, this varying voltage of 20 millivolts, which is being flapped up and down at 400 Hertz into the base. And that is making this flow sort of in a pulsy kind of way. And you can see the numbers going up and down. And that's creating a voltage over here between approximately 1 volt and 7 volt. But it's not completely straight. It's got a bit of a curve to it. Okay, interesting. Now it seems that when we go over here and we've reduced it to 5 millivolts over here on the input, that's made this much smoother, but has given us a lesser output. Yeah, the thing about the the display on these on this extraordinary simulator website is that this is actually a different voltage to that, even though it looks the same. It's a shame that this doesn't scale so that you can see them compared a little bit. I mean, you know what it is because you've got the minimum and the maximum are written on it, but it'd be really good if it was visually so. If I turn off max scale, does that improve it? Let's try that on both. Yeah, that's a bit better. Okay, that looks better. So yeah, if you're on this thing, if you right click it, take off max scale so it's not being maximized, you can now see a bit. I mean, you know, it swings and roundabouts. You could potentially make that bigger, can't you? There we go. Try to make them about the similar. So this one on the left with 20 millivolts coming in, it's creating this slightly curvy but massive waveform. Whereas if we reduce down to 5 millivolts, we're getting a smaller one, but it's straighter and cleaner. Yeah, got that? Cool, yeah, like it a lot. So we have to understand the way the base voltage relates to the amount of current allowed to flow between our transistor's collector and emitter. So we've got a little bit of a diagram here where it goes bugger all, oh my goodness, lots and lots. So that's interesting. Let's keep on going down. So we'll simplify things by removing the resistor between voltage source and collector for now. Here's how the graph works. On the x-axis, we track the voltage applied to the base, and on the y-axis it shows us the measured current. As you can probably tell, the resulting plot looks suspiciously exponential, and that's because it is. In the area between 0 and 600 we only see a super slight increase in the collector's current, but then suddenly it starts going through the roof at around the 700 mark, which you can see here. Yeah, come on, stay with me. No, not going to stay with me. Bleeding mouse. Come on, mouse. You can do it. Anyway. And at around 775 millivolts, we'd see the full amp of current running through it if your transistor hadn't blown up by then. That's because the most general purpose transistors can only handle a few milliamps of collector emitter current. So the actual usable range is somewhere between 0 millivolts and 700 millivolts base voltage. In our amplifier, we're using just a tiny sliver of this, since the scale down and offset signal swings between 560 and 580. Okay, so the swinging between this little bit in here is giving us a tiny bit of ampage coming out. That's what's going on. Now we've got another graph coming up. Look out. So here's what the sliver looks like when we zoom in on it. Now, since we're using a triangle oscillation as our to-be amplified signal, we are basically moving our base voltage back and forth along the curve at a constant speed. So you've got your 560 to 580, so it's constantly going backwards and forwards like that. And so that's given us this increase in current coming out. Okay. So effectively we are replicating the oscillation in the amount of collector current going through our transistor. Yes, as the voltage is changing at the base, we are getting this similar change, this mirrored, not mirrored, replicated change of current. And as we can see, for a rather small change in voltage, we get a significant change in current. Knowing this, it should start to make sense why our setup above works as an amplifier. Yes, small movement to large movement, because the current going through our transistor changes, the voltage at this collector will also change. Because the current going through our transistor changes, excuse me, the voltage at its collector will also change. That's because we are converting more or less of the resistor's potential into actual flow. Right. So again, we talk about potential and we talk about current flow. Let's break this down in detail. So we know that our 20k resistor could potentially pass 600 milliamps in our setup. And on the graph above, we saw that our transistor's collector current is oscillating between 250 and 550. 250 and 550, yeah, beginning and end of that line. So the ratio between actual and potential current flow is also oscillating. All right, at 250 microamps collector current, we are using around 42% of the total potential. All right, and at 550, the number rises to about 91%. Which means that the collector voltage will swing between approximately 1 and 7 volts, right? Giving us a 6 volt peak-to-peak output. This is an impressive amount of gain, because remember, the signal we sent into the transistor's base was just a merely 20 millivolts peak-to-peak. Okay. But what about the distortion? If we take another closer look at the relationship between base voltage and collector current, we can clearly see that the plot is not linear. It's slightly bent. Yes, that's because it's part of an exponential curve. And so as our voltage is oscillating at a constant pace, the current oscillation is slightly speeding up and slowing down. And since this change in current is directly translated into a voltage swing, that voltage swing will be slightly bent as well. What can we do about that? There's only one solution: use a smaller portion of the curve. Oh, right. This helps because the thing about exponential curves is that if you divide them into smaller chunks, they begin to look more and more linear. The zoomed in graph is already a lot straighter than the full curve, but in order to minimize the distortion, we'll have to scale our oscillation down even further. So that's what we saw here, isn't it? So we are going over what we saw in this diagram. The changing of the amount of, the reducing of the amount of millivolts input at the base gives you a smaller amount of amplification, but a cleaner, straighter one. That's what we're seeing in this graph by taking a smaller chunk of it rather than taking the whole thing. It's not perfect, it's close enough. We'll go with that. Good, so those are things we've worked out, I think. Possibly. So the emitter resistor. Right, so we'll just use the voltage divider to scale our input down even further, right? Okay. Actually, there's another way to achieve the same result, but with some added benefits. Adding a resistor between the transistor's emitter and ground. Right, so the other side of the transistor now. I mean, in some ways, all that faff we use. Okay, never mind. Don't overthink it. Don't try to think it. How does this work? Well, this is where it gets a bit tricky. Oh, heck. It works by introducing negative feedback. Interesting. As we know, our circuit operates by having a varying amount of current flowing through the transistor and to ground. Now, if there's no resistance below the transistor, we have a direct, uncomplicated relationship between the base voltage and our collector current. But by adding the resistor, we're restricting the current flow between emitter and ground, and this means that there's again some unused potential here, which manifests in voltage at the emitter. Potential voltage manifests in a voltage at the emitter. Okay. Okay. So without this thing, we get wobbly at the base, and that gives us wobbly before we get to the transistor. Because this wobble here is restricting the flow through the transistor, and that's creating the wobble in voltage here. But then if we put a resistor here, that's also picking up a voltage on this bit or something. Anyway. So how much voltage depends on the two factors, the amount of resistance and the amount of current. Because the resistance is fixed, don't have to worry about it too much. We only have to ask what happens when the base voltage, therefore the collector current, changes. Simple. If they increase, then the voltage at the emitter will increase as well. If they decrease, it will be mirrored there too. Let's play this out with some actual numbers. We assume 0.13. So when do we have to look at this? Have I missed the footnote on that? Yeah. Okay, so before we get into the numbers, let's have a look at the simulation. See if we can wrap our heads around it. So here's our emitter resistor simulation. We've got our 20 millivolt input again here. 20 millivolt input here, this little bit. Got a 20k resistor. We have, although that looks really large, a very small voltage output here between 11.79 and 11.82. Which we would see more or less as a flat line. Okay. But down here, we're now getting a small millivolt output oscillation because of the 10k resistor. Why has it killed this though? Don't quite understand. Says that there. Introduces negative feedback. But by adding the resistor, we're restricting the current flow between emitter and ground, which means there's some unused potential here which manifests as voltage at the emitter. So why are we doing this? There's another way to scale the input. Alright, so we'll just need to go with it at the moment. So with actual numbers, we'll assume the emitter resistor to be 10k, okay. So our base voltage is still swinging between 560 and 580 millivolts. But if we probe the voltage at the transistor's emitter, we'll see that it is also oscillating between 87 millivolts and 102 millivolts. Now, since our transistor's operation, only the voltage difference between emitter and base voltage is what matters. We need to subtract the former from the latter, leaving us with effective base voltage swing between 473 and 578, and voila. Voila. We've reduced it to just 5 millivolts peak to peak. So this negative feedback has reduced this to 5 millivolts as opposed to 20 millivolts. Why don't you just start with 5 millivolts? Anyway, let's not do that. But at the same time, something weird has happened. Yeah, we saw that. To our amplified signal, instead of 5 volts, we're now getting about 100 millivolts peak to peak. Now, of course, we've effectively scaled down our input to just 25% of what we fed into the base before. Okay, going from 20 millivolts to 5 millivolts. But 100 millivolts is not 25% of 5 volts. No, it's not. Something else must have changed. That something is our amplifier's gain. To understand why, we just have to have another look at our base emitter voltage graph. So without emitter resistor, we're using this big chunk of stuff up here, but with emitter resistor, we're down reduced to this thing. Before we added the 10k emitter resistor, our signal was swinging between the 2 points up the curve, but now with the resistor in place, the active range is much smaller. It's also further down the curve, and because it's further down the curve, it's noticeably flatter. That's why our output signal got so much more quiet. By moving the input oscillation down the curve, we've reduced the amplifier's gain. We'll get to the large implications here in a second, but first I want to talk about the added benefits I mentioned earlier, because at first sight this seems a rather bad deal. Yeah, it does. We needlessly cut down our amplifier's ability to amplify, right? Well, yes and no. While we did lose a significant amount of gain, we've also got something important in return: stability and reliability. That's because transistors have two severe flaws. First, if you take two transistors, you'll probably notice that they don't match up. That's because small variations in the silicon they're made of, and those unequal curves are also heavily dependent on the transistor's temperature. Heated up by a few degrees, the amplifier gain shoots up noticeably. Cool it down and it goes more quiet. Which is why all the actual examples and numbers we've talked about so far have been just rough approximations. Your mileage trying this with a real resistor will vary quite a lot, as long as you don't use, that is if you don't use an emitter resistor, because the negative feedback it introduces. Right, let's assume we build the initial circuit twice with two different transistors. One of them naturally has a lot of more gain than the other one. So for the same amount of base voltage, there would be very different amounts of current flowing through each respective circuit. If it weren't for the emitter resistors, the voltage, if it weren't for the emitter, if it weren't, okay, so for the same, okay. So it's saying we've got two transistors, same transistors, but one of them has a lot more gain than the other. Now, since the potential amount of current on the right side is a lot higher, because it's higher gain, we'd expect to see a significantly larger voltage at the emitter. In reality, though, both emitters will be just a few millivolts apart. 74 to 88, 87 to 102. This is because the more the emitter voltage increases, the smaller the difference between the base and emitter becomes. So as this increases, this feeds back, making this smaller. Oh. So the more the emitter voltage increases, the smaller the difference between the base and emitter becomes, reducing the transistor's gain and therefore the collector current in the process. As we've seen before, very small reduction in base voltage can already give you a huge reduction in collector current. Okay, so we're essentially turning the transistor's gain against itself. The more gain the transistor has, the stronger the negative feedback and the more the gain is reduced. Conversely, if the transistor's gain is rather weak to begin with, then the negative feedback and thereby the gain reduction will be weaker as well. To illustrate this, I've drawn up 4 different plots. Oh heck. So what it's saying is that this emitter resistor creates this negative feedback which controls, or better manages, the varying gains of transistors. I think that's the key to what we're getting at. 2 of them show the base voltage to collector current curves for our example transistors without negative feedback. That's the 2 huge spiky ones. The other 2 are what we'd measure with a 10K emitter resistors in place. For better comparison, I use a little trick here. Instead of measuring the actual voltage between base and emitter, I measured the voltage between base and ground. Okay. This way we can integrate the negative feedback directly into the gain curve, and as you can see, and as you can see, the rather significant gain disparity between the 2 transistors is pretty much limited by the negative feedback. Hurrah! Good. Which is why they'll perform in a very similar way in our example circuit. But that's not the only benefit. Transistor's temperature has an effect on its gain. Normally that effect is quite strong, but the negative feedback again really mitigates it here, because as the temperature rises, the gain attempts to increase, which in turn will raise the emitter voltage, and that dampens the gain in response. One final question remains: why did I pick a 10k resistor and not a bigger one? Well, if the negative feedback is so beneficial, why not use a ton of it to negate all differences between transistors and eliminate any temperature dependence? Simple, because we'd be completely crushing the gain, making our setup basically unusable as an amplifier. So in the end, choosing a value for the emitter resistor is always a balancing act. How much gain are you willing to give up for reliability and stability? I don't know. Yes, got it. Yeah, got that. Understood. All right, so we're on page 18, 19, and you've got to get to 30, really, and it's 9 o'clock. That's an hour and a half. We're all right. We're on track, I think. I think, with a bit of luck, there's a bit more breadboarding coming up, which will be nice. Let's just skip down a little bit. Yeah, look, there's some. Okay, so we're nearly to that point. So, gain-changing tricks. So the emitter resistor is not the only variable we can mess with. We've got two more options. First, we can adjust the value of our collector resistor. Oh, I back up that end again. Okay, because if we increase it, then we'll reduce the amount of current that could potentially flow through it. Now, since this does not affect the transistor's operation, the collector current swing will stay the same, which means that essentially it's swinging across a larger proportion of the full potential, netting us a bigger voltage swing at the output. If I stay the same, current staying the same, if current stays the same, there is a hard limit here. We can't just keep increasing the collector's resistor value in the hopes of unlimited gain. Okay, so if we increase the value, V equals IR, voltage equals the resistance times the current. So if the current is the same, if you increase the resistance, the voltage increases. Okay, good. Whew. My old physics teacher would be proud of me. Now, I get the feeling there's probably a thing we can look at this point. Yeah, there we go. Let's go and have a look at this thing here. Oh, crikey. So gain changing tricks. Oh, yeah, no, it is. I can zoom in. How do I then move about on this thing? Space or shift drag. Select, drag, select. Oh, poo. Alright. Anyway, I'm sure we can see enough. So a 20k collector resistor. So that's the one before. That's the one at the top. Collector resistor. 20k. We get an output between 11.8 2 and 11.7. Stick in 100k and we get out 10.98 to 11.1, which is not massively more, but it's still more. Put in 1 meg and we're starting to actually see a waveform. How do I... Oh, if I do that, it just really kills it. It's because I don't have a keyboard attached that it's really given me a bit of trouble right for that. I can't... Can I... Is there a middle button? No. Alright, we'll just go with it. But we get the idea that as we increase the resistor here, you get a bigger range of voltages coming out of this end. Cool, back to the manual. Because at some point the potential amount of current will drop below the set collector current, starving our transistor of power and distorting or killing the oscillation. So if you go too far with a 10 meg one, you're just not getting enough current through and it will start not to work. So what's the second option? Well, this is where it actually gets interesting, because the second option is adjusting the constant base voltage that our signal is riding on top of. Up until now, I've been using a 20 millivolt peak-to-peak triangle oscillation with a DC bias of 570 millivolts. Yes. So on our adjusted curve, we were moving backwards and forwards across this tiny marked section. Now what we could do is move that section down the curve to where it's significantly less steep. Right. Since this will have a direct effect on our collector current swing, we should also see a reduction in gain. Why do we want to do that? But while we could go through the trouble of adding our scaled down input signal to a variable DC bias before applying the sum to the transistor's base, there's a simpler, more elegant solution. We like simple and elegant. That's our favourite thing. So instead of adding the bias at the base, we can subtract it from the voltage below the emitter resistor. Okay. Because remember, the only thing that matters for transistors operation is the voltage difference between base and emitter. And by pulling the emitter's resistor's south end below the ground, so below 0 volts, we can expect the voltage at the emitter to drop proportionally too, because of the negative feedback bit. This will increase the difference between base and emitter voltage, which in turn should push up our amplifier's gain. To try this out, we'll first set up a potentiometer as a variable voltage divider. This will be our control voltage source. Then we'll invert and scale down that control voltage with an op-amp. By turning the potentiometer, we can now adjust the voltage at the op-amp's output to any value between 0 and 7. Going any more negative, 0 and minus 7, going more negative would increase the collector current too much and starve our transistor. Lastly, we need to scale our input signal down to appropriate levels, since the intention here is to pair this circuit with Eurorack compatible oscillators, which use 10 volt peak to peak. So I'm using a 100k 100 ohms voltage divider for this purpose. This way we're effectively feeding our transistor a 10 millivolt peak to peak input. This is an active one. Alright. There's a lot about this last page that I don't quite understand. I'm afraid. A lot of things have been said in this bit that kind of make it sound like I should have gathered all these things by now. Because like the only thing that matters is the voltage difference between base and emitter. I don't know, I don't quite understand that. I know that this negative feedback thing had an effect on reducing the base voltage. Alright. So what I'm going to do at this point is we'll switch back to the breadboard, we'll build it up and see if we can demonstrate these things that we are trying to get our head around. And I mean, I totally grasp the idea that we're trying to find a small amount on this graph that's going to be as flat and as stable and repeatable as possible. And everything that we're doing is trying to make that stable, reliable, because we need this symmetry and linearity to some degree, so that we know what's going on, regardless of how flaky our transistor is. That seems to be the gist of it. So let's do some business on our breadboard. Now to do this we're going to need to set up some power with our batteries. So we'll do that first. Let me show you what that's all about. So let me swap to the overhead. undeterred. So 9-volt battery and one of these. They usually just come with a little bit of cable sticking out, so I've soldered on, I think I have, the ends of some patch wires so they go in better. Otherwise they kept falling out like they did when I did the VCA all the time. So I'm going to stick that cap on. Now we need 2 of these in order to create a situation where we have plus and minus 12 volts. And we can do that, it's actually in here on page 32. So on page 21, let's pop down to page 32. Okay, using 2 9-volt batteries as a dual power supply. So he talks about a dual power supply. I don't know what that is, but we're going to do something with batteries. We've got 2 batteries and clips. And this is what we do. So we take the positive of one and plug that into the one that says positive. So that's going to be our... now mine are labelled differently to his. His seem to be minus on the top and then plus. And then minus and plus, whereas mine are the completely opposite way around. That's fine, don't worry about such things. Just know what it is that you're doing. So, I've done that completely wrong. No, I haven't. So, positive goes to positive on that top rail. Am I going to make this difficult for myself? I need to match up what he's doing. I need to match exactly what's going on here and ignore the markings on my breadboard, because I'm then going to be following the diagram on here and I will stuff it up if I've done that incorrectly. So, what was I saying? So the positive on one battery needs to go directly to the inside rail. Doesn't matter whether it says negative or positive on it, but the positive one is going to go to that inside rail. The negative one goes along with the positive one of the other battery to the inside rail on the other side. Now we need to take a patch wire and connect this negative and positive up to the top rail, like so. And then finally the negative one goes at the bottom. I think that's right. So we now have a positive 9 volts on this rail, and we've got a ground going across the top and across the top here. I'm not going to use a red one, I'm going to use a black one. Do I have a sensible black one? No, I've just got ridiculously sized black ones. Oh, this one's it. There we go. So that there is ground, and I've got minus 9 volts here, positive 9 volts there, ground and ground. Yeah, I could spin the breadboard around, but then the other numbers are different. I'm not just trying to be awkward. That's just how it is. I could spin it round, like I say, but then these other numbers, and that threw me as well. But then maybe that's the better option. So, all right, good advice there from the crowd. I'm going to spin this round. So then my numbers are backwards. That's okay. take all this out and start that again. So at least then my power is going to be more together. Right, so this way around. Are you still with me? 9-volt battery. Taking the positive, sticking that into the plus there. I'm taking the negative side and putting that into the negative. It does make more sense, without a doubt. From the other battery, I'm taking the positive and also plugging it into there. And I'm taking the negative side, the black one, and plugging it into the bottom. And then taking a cable to take this negative rail, this inner one, to the negative rail at the top. All right, good, done. Back up to page 22. There, okay. So the negative rail, it says, is at the bottom. That inner one is ground. That top one is ground, and that's positive, negative. Even though it says positive on it, that's what it's trying to say. So we get ground, ground, negative, positive. That's what we've got. Good, right. Super. Are you still with me? Good. Right, let's plug this thing in. So we need to take one of our chips. I'm going to take my magnifier so I can see what's going on. You tease it off the stuff. Where's my magic squishy? Where's my squishing thing? There. I've got this very cool tool which allows me just to straighten the legs a little bit. Should help it go in a little bit better. So make sure that the TL072 chip, which houses 2 standard op amps, is exactly set up. If you reverse it, it will blow up. So it needs the little hole on it there. That doesn't need to sit anywhere in particular. So I'm ignoring the numbers down the side because mine are opposites, different. Just sticking it there. There's the little circle on it there. That's the way around it goes. Pop it in. Okay, good start. Now we need our pot. Just going to sit over here a little bit. A little bit of space between the two. Doesn't matter greatly. No, so pop that in there. Like that. So let's put some wires in. So this edge here is going over to the positive rail. Then one pin on this. Is going to the ground, which is the top one. And the other one is going to the positive rail. So I'm actually going to change that because I like the symmetry of the colour. So that pin there is going to positive. And it's not the middle pin, it's the right hand pin. In a gap in between. It's going to negative. Good. That's those 3 bits done. I need a 100k resistor from earlier. This is jumping the fence in between, using from the middle leg over there. And then using a patch wire, this is patching itself into this second pin on this side. I'm not sure of the pin numberings in this particular situation, so I'm just describing it as I see it. It's probably, if this is this probably pin 1 here, 1, 2, 3, 4, 5, 6, 7, 8, probably. Not sure, but it's this second pin on this side, goes into there, and that matches up with that 100k resistor. So far so good. In fact, what I could do is take the power out while I'm putting these things in. I think that would be wise. Like so. Okay, thanks everybody. Yes, taking the power out is always definitely a good idea. Okay, did that. Let's finish up on this side. So we've got a big one going from the first pin. And we're taking that just over here out of the way somewhere for the moment. Then we want an 82k resistor. 82k. 82k, that one. Now this is going between two parts of the op amp, pin 1 and pin 2. I believe, just like that. Then a couple of patch wires, which is taking pin 3 to ground. And pin 4 to negative. Alright, so this is all the op amp side, the side of which I don't know what any of that's doing. This is to do with pulling voltage off the emitter of the transistor. Okay. That's what all that is about. Now moving over to the transistor, we've got 4 of those here. We can pop this in anywhere, but this cable here is going to be jumping over to the third leg. You can see which way around it goes because of the shape of it. So that's the base. Is that then the collector and that's the emitter? So is that going to the emitter? That's connecting up to that. That would be right. Okay. So I'm going to follow this up here. Stick it in there. This right hand leg is the emitter. We're taking a 10k emitter resistor. Yeah, see? I've been listening. 10k emitter resistor to take the emitter to this other weirdo circuit that's doing stuff, the op amp circuit. You know, the word op amp would make you think, well, that's an operational amplifier. Why don't we use the amplifier as an amplifier? Anyway, let's not worry about that. We're using an op amp in order to do something crazy to the emitter leg. So it's got that going on. So from here, I've got a socket this way round. Yeah. I've got a 20k going to the collector. 20k, this one. And that's going to positive, because that's our positive voltage coming down through a 20k resistor restricting the flow to the collector at the transistor. Right. Now we have to do something clever at the base in order to create this oscillation, presumably. So for that we need 100 ohm, which is one of these. That goes to the base and goes to ground. But we also have 100k that's going off sideways into our patch socket. So that also takes on the ground like that. So those two are having a little bit of a voltage divider going on between them. That's going to a leg on the patch thing. And we've got another wire going out to ground from the ground of here. So around the transistor, all we've got is this emitter thing. We've got the input. Voltage divider around the base. And then we've got all this garbage around the emitter. And we've got an output. Right. So we did all of that. Is that all there? If I missed anything. 1, 2, 3. 100k to there. To there. That's in there. That goes across, that goes across. No, that looks good. After you've built this, connect an oscillator to the input socket and your oscilloscope to the transistor's collector. Oh, okay, right now. Here we go. Here we go. So, right, plug my power back in first of all. So this one goes into positive over here. And watch for smoke. This one goes in between the two, like so. Now we need to connect an oscillator to the input. So I had an oscillator here. This is my input. That's plugged in. And I need to put my oscilloscope to the transistor's collector, which is the amplifier's output. Because when we were going back up, the voltage that we were getting was coming off after that resistor before the collector. So I need to get a scope into after the resistor into the collector, which is approximately there. And I'm going to need ground, which is one of these things here. Plug that in. Right, so now with great excitement, I can bring in my little scope. Look at this fella. This is excellent. So let me try to get this into shot if I can. Have this a little bit like that. Get those batteries. Get out of the way. Have this in here somewhere. So this is a DSO 138 Mini. I bought it from China. Just popped over to China to get hold of it. It is, you can get, there's a couple of different versions. This is the Mini. I like the Mini because it can be USB powered, which I tend to have USB power knocking around the place, as opposed to having to find some kind of 9-volt wall wart for it. Potentially, I could also Eurorack it with a little bit of the right cabling, but all I need is a little USB cable. If I can find the input. It does come with a little box you can put it in, but you know, I just like fiddling around with my fingers. Plug that in there. It cost like 20 quid, 25 quid, something like that, maybe 35 with delivery. Took about 10 days to turn up. And this is going to allow me to do proper scope testing here, as opposed to trying to use a Eurorack module, for which it just gets complicated. I also like the fact it has crocodile clips rather than some other ones have other things which aren't crocodile clips. Crocodile clips seem to be sensible to me. So I've got a positive and a negative. So my assumption is going to be I will attach my scope to there, to ground, and to the signal coming off the collector. It seems slightly counterintuitive, the fact that it comes off the collector as opposed to the emitter. You imagine the output to be after the emitter, not before the collector. It just feels weird. Now I should point out that I've used this for about 2 minutes and I don't really know what anything does. So what I kind of hoped was that I'd plug something in and it would just work. I mean, certainly I've had audio signals from the oscillator on here without any bother at all. In fact, let me do that to start with. So yeah, I'll put something on there and put something on there. Do you see that? Look at that. Isn't that beautiful? So that's my oscillation coming out of my VCO. Superb. Superb. It's a great little scope. So I know it works. Question is, what is it I'm trying to measure here, and do I have the knowledge to know how to get that on the screen? I have buttons I can press. Oh, I think it's offset is my difficulty at the moment. So just bear with me. There's definitely something there, look. I'm just going up higher and higher in time, and that's not going to help. But that looks like a good one of those. So I'm going to go along to here. And press things randomly. I need some kind of offset. That I think is offset in the wrong direction. Let's try it this way. Now, if anybody in the audience can tell me, no, what? Valves? What? If anybody can tell me what I'm supposed to be doing, that would be awesome at this point. See, that felt like it should have done something really helpful. Hold. I don't want to be on hold. Running. Okay. What select am I on now? Oh, there's something. Alright, well I might have fudged it. There's definitely a line. The line's going to be good. I need to blow it up. That's 0.2 volts. That definitely won't. That's 2 volts. 0.2 volts, 20 millivolts. 0.2 volts. 0.1 volt, 0.5 volt. Change the scaling. Alright, I'm not going to waste too much time on this. And someone said, yes, I shouldn't be getting a reading yet. Okay, fair enough. Well, I had something a minute ago, didn't I? There. So I'm just going to leave it at that for the moment. Right. Unfortunately, the results won't be particularly useful. Awesome. So after you've built this, connect an oscillator to the input socket and your oscilloscope to the transistor's collector, which is the amplifier's output. 17 it says, so there's a footnote to this. Then try adjusting the potentiometer to change the circuit's gain. The results won't be particularly useful. So, alright, look. See that? It's moving something about. So we are seeing a change in voltage as I move the potentiometer. And you can also see that there's a wiggle to that line, which I imagine is the is the wiggle to the line. If I put that right in the middle, does that help me at all? 5 volts, 2 volts, 1 volt. Not really. 0.1 volt. Can I still bring that into play? It's not really giving me anything other than sort of wobble at this time. Right. So there are two okay, 17. Let me just have a look down to see what the footnote is. If you don't have an oscilloscope, okay, watch me demonstrate this. Oh no, we're not going to be tempted to do that. Not quite yet. Might do in a minute. Let's see how we go. So there are two major problems. For one, the output signal's DC offset seems to be tied to the set CV and is moving about wildly. Also, the gain added by increasing the CV is so minimal, it's actually near impossible to see the oscillation without zooming in massively. Now, this is the first time CV has been mentioned. So where has CV come into all this? Simpler, more elegant solution. Instead of adding bias to the base, we can subtract it from the voltage below the emitter resistor. We've got a voltage subtractor. This will increase the difference between base and emitter voltage, which should push up the amplifier's gain. To try this out, we'll set up a potentiometer as a variable voltage divider. This will be our control voltage source. should need to put capital letters CV source, or in brackets or something there. This will be our control voltage source. So the pot is controlling the voltage. Then we'll invert and scale down that control voltage, of course, with an op-amp, obviously. And by turning the potentiometer, we can now adjust the voltage at the op-amp's output to any value between 0 volts and -7 volts. We can now adjust the voltage at the op-amp's output. Okay. Going any more negative would use too much current. Scale the input down, which you're doing at the base using a voltage divider of 100k and 100 ohms, which given our transistor 10 millivolts peak to peak. Alright, okay. So then going back here, the output signal's DC offset seem to be tied to the set CV. Yeah, so as I move this knob, that moves about. Sorry, my fingers are in the way. And the gain added is so minimal, it's actually near impossible to see the oscillation without zooming in massively, which I don't fully understand how to do on my scope. So what's going on? So let's talk about the output signal's DC offset. Why does it move around so much? We already know the answer, do we? What we're doing by changing the emitter voltage is moving the operating region further up and down the base voltage to collector current curve. By doing this, we're not only changing the amplifier's gain, we're also changing the average amount of collector current that will be flowing while the amplifier is operating. Whoa, how are your brain cells moving? And the more current is flowing on average, the more of our 20k resistor's potential is used up on average. I use the word potential again. Meaning that the average voltage at the transistor's collector is changing as well. So effectively the amplifier's gain is directly tied to the output signal's DC offset. So we're measuring. Okay, try to compensate for that, right? We could of course turn on AC coupling on our oscilloscope. Alright, I can do that, I know that switch. That did nothing. Well, that appears to have done less, if that makes sense. It's not that one, is it? See, I changed something, I offset something myself, which I thought I was doing. I thought I was being clever. Just going to put that back to the middle in case that's skewing everything. So I don't strictly know what that's all about. So, yeah, if I put it to AC, it's much less flapping about. Put this back to DC. And it goes all the way up there and all the way down here. Okay. I can come out to 2 volts. $5 volts. To AC. Okay, hope you're getting all of that. This will remove any DC offset from the VCA's output. Since our oscillation is now semi-fixed to the 0 volt line, you can turn up the scaling so you can actually see what's going on. I'm not really seeing anything, although that was just pulled out there, so that might have a factor. That going in. If I go back to the zoom in side of things, bring this back to the center, attempt to zoom in, 10 millivolts, oh, blew it. Ooh. I'm unsure if that's what I'm supposed to be seeing. Oh, look, look. Okay, it's coming together. I'm getting a shape. That's a good sign. So if I pull this out slightly, does it all disappear? Yeah, okay, so it is something to do with that. Interesting. Right. It's a bit hard to tell through the noise floor, seeing that, but changing the CV really does have an effect on the gain. Unfortunately, the range is definitely way too small. This shouldn't be surprising though, shouldn't it? Because if we look at the base voltage to collector current curve again, we can see that the steepness and gain level only changes slightly in the area between 400 volts, millivolts and 450 millivolts base voltage. Beyond that, the emitter resistor is preventing us from increasing the gain at all, since it bends the curve into a straight line. On top of that, the AC coupling is not a perfect solution for removing DC offset, because as you're changing the gain, you can see that the signal goes off center for a little while. Yeah, that's just how AC coupling works. Because of these two problems, our simple circuit doesn't cut it. But we can salvage it by adding a few extra components. Well, that's good. Thank goodness for that. Good, right. Okay. The differential amplifier. Right. Wow. So now it's really interesting how this is kind of an exercise in showing us what doesn't work before giving us the answer, in the hope that we will understand it as we go. It's risky, and I do partially understand some things, but it's a challenge, man. It's a challenge. Right, let's keep at it. The first change we're going to make looks very confusing at first glance. Basically copying and pasting our transistor and its collector resistor while connecting both emitters to the same original emitter resistor. Whew. Also, we're directly grounding the new transistor's base. What's this supposed to achieve? By doing this, we are turning our regular amplifier into a differential amplifier. Don't worry if it doesn't mean anything. We'll get through the circuit step by step. Right, there's a footnote down to 18 at the bottom. We have another simulator. We can go and have a look. The differential amplifier. So, wow. This is really interesting. This stuff here being pulled away at the bottom. There's your pot. So I change potentiometer 1. Go all the way one way and nothing comes out, all the way the other and we get the biggest swing, I guess. Difficult to see exactly. Very interesting how this is all being pulled away. There's a voltage divider here which goes into the base, and then this negative feedback is somehow doing something else to this. Our input is plus or minus 5 volts. Gee, flipping whiz, I don't know. So how does it help having this other one here is the question. Now there's something exaggerated over here, which kind of means it's flashing from one to the other. How does that help? I do not know. Curious. So let's read what it's trying to tell us. Okay. So by directly grounding the transistors, okay, we're blah, blah, blah. So essentially we're exploiting two interlinked mechanisms here. First, without any input signal, there are two stable identical currents flowing through our transistors. Point 19. Assuming the transistors are closely matched. All right, yeah, we'll make that assumption. That combine at their emitters and are then sunk by the op-amp. Yeah. You could call this our total bias current, which directly depends on the voltage at the op-amp's output. So the without any input signal, okay, so with nothing flapping around at the base, then the only changes to the base are going to come from the changes in this voltage at the op-amp from the emitter resistor sync thing. Sync. The more negative the output goes, the stronger the total bias current will become. This is because both transistors' bases sit at or around 0 volts while the VCA is operating. And the bigger the voltage differences between their bases and emitters get, the more transistors will open up. The bigger the voltage differences between the bases and emitters, the more the transistors will open up. Second, and just like before, we apply a heavily scaled down version of our input signal to the left transistor's base. As the input signal oscillates, the bias current on the left hand path will start to oscillate as well, simply because we're further manipulating the voltage, yeah. Now as the bias current oscillates, it forces its twin on the other side to oscillate as well in an inverted manner. Oh, okay. This is because of the negative feedback created by the emitter resistor, which resists the current going through it. Since it's easier to force the right resistors to close down or open up than to increase or decrease the total bias current, the former will happen. This means that the total bias current will stay roughly constant, while the two individual collector currents fight each other for real estate within it. Yeah, okay. Now the trick here is that if we increase or decrease the total bias current by changing the op-amp's output voltage, okay, we also change the transistor's gain levels. The trick is if we increase or decrease the total bias current by changing the op-amp's output, we also change the transistor's gain levels. This is simply because the more current is already flowing through a transistor, the more sensitive it becomes to changes in the base emitter voltage. Crikey. So as the total bias current increases, the two collector currents will oscillate more heavily, causing the collector voltages to oscillate more heavily as well. All right, I'm losing my ability to withhold, to absorb this information, I think. Turn a little bit of heat on. What time are we on? 10 o'clock. Okay. We're not far away, you know, we're not far away. You'll have more current on one side than the other. Okay. Cool. So I think we're probably going to move to doing what it is that's being asked of us on that bit. Finally doing this signal subtraction to that bit, and that's it, it says. So look, we're a couple of pages away. So if you're starting to lose the will to live, that's okay, we're nearly there. So the trick here, if we increase or decrease the total bias current by changing the op-amps output, we change the resistors, the transistor's gain levels. It's simply because the current is already flowing. All right. So we get as much gain as we need, since we're not relying on the steepness of the curve anymore. Also, if the collector resistors are matched, the collector voltage oscillation should be the same, just inverted. Okay, sorry, I've become detached now. I can't quite grasp it. So the DC offset should be identical as both collector currents swing across that same midpoint. I'll have to go back and reread all of that. So we're going to have a look at this. We're going to build what it says on here. Look at the oscilloscope and see if we can get something sensible out of it. Thanks, Ken. I appreciate the encouragement. So we have some extra things to add to our circuits. Let's take our scope out for the minute. And pull out our battery. Going to go, what are we looking at? Are you overheading or are you manually? Okay, back to the overhead. Right, let's see if we can sort this out. So this bit here seems to stay the same. That's the same. That's the same, 100k. Our 82k thingy there, that's the same, that's the same. So okay, so our sunk is syncing the same. Here, I'm assuming that's the same. Right, we had a 20k. Okay, so yeah, right. What's that? That's the emitter. I have to pull that out for the minute. So we had our 100k and our 100 there, and that's our 20k from the collector. Now we need to put in a patch wire from the emitter. Here's number 3. And plug that into another transistor which is going to go in alongside. So emitter to emitter. Right. So transistor. Emitter to emitter. So why is there a little cable going off for the 20k on that one? Is it just simply because it was going over a thing? I think so. So 20k. 20k. Goes to the collector, to positive. And we need the base to go to ground. That's it. So I've just put in another transistor which is connected on the emitters. It has a 20k input and the middle goes to ground. Look at the circuit. 20k, connected to emitter, ground. So we get inverted outputs. Oh, it's swinging between the two. Let's put this back in. I think that's good. Put our power back in. If you connect the oscilloscope to both collectors on separate channels, what? Should be able to verify our assumptions. Alright, we've made some assumptions. Shit. Right. So, collectors, both collectors. So collectors are the first one after the resistor. So there's one collector. After the resistor, there's another collector. So, if the collector resistors are matched, the collector voltage oscillations should be the same, just inverted. So what I'm looking for is an inverted output. So, let's put that back up here. Come on, you bloody thing. Right, that's on there. Now I've got to find this thing again, haven't I? Possibly. Oh, I'm on 10 millivolts, so let's... Oh, my battery's come out. Let's put that in there. Ooh, look at that. That's interesting. So that's a ramp down. That's a ramp up. You can't see that. Let me try to improve upon that. Right, you got that? Yeah? So, is this still doing the offset a little bit? That's as far down as that goes. Let me zoom out a little bit, if I can remember how to do that again. Not quite like that. That's the wrong way. So I need to wrong button. Anyway, that'll do. So, as you can see, there's a ramp up going there. Ramping up, that's on the original. And then it's a ramp down coming out of the second one. So I've got this inverted waveform coming through from this differential amplifier. It's a much nicer signal than we had before, so something has been cleaned up about it, which is interesting. I'll leave that connected. So what does this mean? So both signals are moving downwards as their volume increases. Both signals are moving downwards as their volume increases significantly. Both signals are moving downwards. So is having two signals tied to the DC offsets better than having one? So this still moves about if I move this. And are we back on DC or should we be on AC? See, that's interesting. So I suppose if you're in DC, no, I don't know. Okay. Both signals are moving downwards as their volume increases significantly. I don't know what that means. Now I've zoomed in a bit and you can see they are inverted copies. We can see they're inverted copies. Yes, absolutely. I don't understand the moving downwards bit. So, signal subtraction. So here's the twist. If we take our inverted twin signals and subtract them from each other, the result will be a signal without any DC offset, right? Possibly. Well, since both original signals have the same offset, they'll cross each other exactly at their respective midpoints. All right. Yeah, okay. I can see that, yes. This example, it's witchcraft, yeah. This example would assume that this would be right on the 6-volt line. Now if we subtract 6 volts and 6 volts, we get 0 volts. Yes, the two signals will diverge, which means that their difference increases, then you get your peaks and your valleys and you get your waveform back. Got it. The best thing about this is that it works regardless of what the exact DC offset is, as long as it's the same for both original signals. Okay, so how do we subtract the signals? So hopefully this is going to put it on the right place in our flipping oscilloscope that I'm keep messing about with all over the place. And this is about so having this differential amplifier creates an inverted version of itself, because it's kind of, it's like you've got these two pumps next to each other. With these transistors, and as one pumps, the other one sucks, the other one sucks, the other one pumps. It kind of it has that sort of relationship. So you have a waveform and you have an inverted waveform, and then because there's this weird DC offset which is driving us nuts, because you've inverted it, like the same you would using balanced cabling. You know, you pick up interference, you then invert them, put them together, they cancel each other out. But they don't cancel each other out because of this DC offset, and it's the offset that gets cancelled out when actually their waveforms get added together, which creates a bigger waveform. If they were revolving around 0 volts, then they would cancel themselves out to 0 volts, but they're not because they're offset. I think. Right. So how do we do it? Simple. Another op amp. Well, that's handy. We've got another one in that here chip here, haven't we? You might want to look at the simulator. I don't know that I do. But all right, let's do it. Let's do it. Let's do it. In for a penny. Whoa. So, what the heck and all is going on now? So what we've done is we have our sink over here, which is pulling stuff away. That's controlled by that's our CV control of our amplifier. So we want that to turn that up and turn that down. Should be giving us an amplified signal. Should be giving us our volume control. Should be doing here. And the way that it's working is by pulling stuff away as a negative feedback into this here transistor, which is regulating the flow. That is also flowing in this other transistor, which is set in opposition to it to create a differential amplifier. That differential amplifier's output needs to be added together in order to remove the offset. I can't remember where the offset came from, it's just something that's there. And this op amp here, with 100k watts it and 100k thingy there and a couple of 100k's in there, does the business. Sorted. Sorted. And as we change this, yeah, you see it goes down and it gets bigger again. If I No, that isn't scaling, that's good. It's big, small, because it's pulling less and less away. Isn't that brilliant? That's really good. These are fabulous. They are just fabulous. So this is what op amps do. They subtract the voltage at their inverting input from the voltage at their non-inverting input. Great. And after that, they multiply the rest by a fixed internal gain. Because an op amp's gain is huge, we have to take some measures to calm it down. If we really want to subtract our two signals without changing the signal's amplitude, we can set our own op amp as shown before. Here's how it works. Let's first imagine that both input voltages are the same. Since two resistors with a non-inverting input form a 50% voltage divider, we'll measure 3 volts between them. Yeah. Now for the op amp to enter a state of balance in this scenario, the voltage at its inverting input would need to be 3 volts as well. The only way that can happen is if the op amp's output sits steady 0 volts, because then both paths are exactly the same. Two 50% voltage dividers with 6 volts on one end and 0 on the other. Okay, but what happens if the two voltages start to diverge? Let's assume the bottom voltage now sits at 7, while the top one is dropped to 5. This means that the op amp's non-inverting input reads 3.5. Now, since the op amp wants to get the other input up to the same value, the output really can't stay at 0. Instead, it will have to make up for the difference between the two input signals. To do that, it will push out a steady 2 volts, because that's the midpoint between 2 and 2 volts is 3.5 exactly. Oh, okay. Let's add this to our circuit and see how we fare. I don't know, I'm wearing myself out, but we're nearly there. Damn it, we're nearly there. And that's it. Okay, nearly there. So nearly there. So we're employing this extra op amp. What are we sticking in that's new? A bunch of 100Ks, aren't we? So get out of it. Right, concentrate. So into this space. So that's my 20K. Now that's why there is an extra, you put in an extra cable for that 20K that I haven't put in yet. No, we still don't need to. No, it's only because of that. Right, so we need some more 100Ks. Got 2 more here. So let's take that out for the minute. So there's 100K. That goes from the under the 20K. So it goes from the collector so it goes next to this one. So on the collector to that first part of that op amp. Stretch it over to there. There's another 100K that goes to ground from that. And one more 100K. Blue one this time. Probably not a good idea. Thinking about it, don't think about it. Goes to pin 2 from the collector of this one. That needs to behave. That needs to go up there. Keep this nice and straight. That needs to go there to pin 2. And there's another 100k that goes between 2 and 3. I've already got the output of that going to something. So let me go back up to this diagram. 1, 2, 3, 400Ks. There was a better. Where was the? Oh, it was here. So we want collector. 100K collector goes to one part of the op amp. 100K collector, the other one goes to another part of the op amp. 100K goes to ground, and the other 100K goes to its own output. Yeah, that's right. No other additions, were there? I don't think so. How am I going to be able to measure this? So we're measuring. Oh, we know we could be measuring at the output of the op amp. I'm not entirely sure which one that is at the moment. Let's not worry. You should now be able to pick up a properly centered signal from the subtractor op amp's output, which is the second pin from the left on the upper pin row. Thank you. Very useful. Thank you. Second pin from the left. So that one there. Second pin from the left. Right, right. So let's put this back in. Like that. Could do with a better fit, couldn't I? That's that. The reds back in. Ooh! Look at that now. There we have a decent signal. Now if I change this, it goes away, it comes back. So that So, so with all this garbage on here, right, what I've achieved is the kind of the same, the volume knob that I had right at the beginning. That's what that feels like a little bit. But of course, obviously, it can't possibly be that. We've done a whole load of other stuff, and it's really exciting and interesting, and all of that. But it just, you go, that's kind of what I had at the beginning, wasn't it? Anyway, so we should be able to pick up a properly centered signal, yes, at the subtractor op amp's output, which we can. Second pin from the left, yes. Hook up the oscilloscope, check it out. Make sure the AC coupling is turned off. Okay, thank you. Didn't say that before. Right, now we're on DC coupling. Right, so that's proper now, so there's no DC offset we're having to deal with. It's now doing it for reals. If your signal still isn't properly centered, this means that your transistors are not tightly matched. Well, and also my oscilloscope's a bit all over the place. But not to worry, we can compensate for a bit of mismatch with a very simple but effective addition to the circuit. Okay, we're not quite there then. Eliminating mismatch. Darn it. Okay, a little bit more of an addition. Ooh, something pouring out of this base here by the looks of things with ups and downy arrows. That looks a bit scary. You can replace the pot with control voltage. Right, okay. Yeah, gotcha. Moritz has left us. Thanks ever so much, Moritz, for being with us. That's been extraordinarily useful. I'm sure in the comments that's been helpful as I've been agonising over here. You've been smoothing the way in the comments, and that's extremely awesome. We're very nearly there now. So instead of connecting second transistor's base directly to ground, we'll give it a very small, constant, near zero voltage via a precision timer set up by a variable voltage divider. By doing that, it's as if we're changing the transistor's natural gain level. Positive voltage simulates more gain, while a negative one simulates less. And it's this natural gain level that will be ideally identical between the two, because then their voltage swings would be exactly the same. Okay. So we are sticking something else in at the base of the one we hadn't stuck something in before. All right, so we've gone through there, 100k, a thing over there, some kind of pot. Okay, so let's just pull out any things again. Then we'll try to get this done. Try to get this done. Keep at it, you fool. Back onto that screen. Right, so according to our circuit diagram, we want a couple of 100Ks coming off the base and some potentiometer thing in here going to positive and negative 12 volts. So we've got 100K again. Coming off the center of this second one here. So this second one, we've already got, what else is coming off the center of that? At the moment it's going straight to ground. Yeah, we don't want it to go straight to ground. We want it like this one having 100, but we're also taking 100K across the divide over here. So we need, that's an 82, 100 ohm, which is this one. And this goes across. So we had this ground here. We'll take that cable out. And going to ground, which is the top one. So I want that in between one, which is the 30. Oh, got a bit blowy. The rest of my family are going to be huddled under a table somewhere. Flippin' heck. Right. So there's 100 that way, 100K going that way. a nice big wire going from the end of that 100k over to past here. Doesn't really matter whereabouts. Put in another wire which goes all the way to positive. There. We get one of these. Stick that in 1, 2 and 3. And finally, I think, take the first 1, 2 and 3. Take that one to negative. That should be it. Well, that seemed to kill it rather. Your bins are blown over. Yeah, I'm a little worried. Flippin' heck. Okay, don't panic. Focus. Perhaps. Let me go back up to the there's 100 and 100k. Then we've got this thing which goes up and down. So if I turn this thing, yeah, not sure entirely what's happening. Let's see if I can just see. Is that in the right place? Probably not. Right, I have to get my glasses on. So the 100k is going to ground. Just that one. Let's go into there. Three. That goes to positive. That goes to ground. This goes over to the 100k. Anything else over there? No, that's still going to the 10k. This going to negative, which is kind of, yeah, no, that's right, negative. Okay. Fiddling with the trimmer's setting output signal to get the waveforms mid-axis exactly right. I seem to have lost a lot of stuff. Where's my voltage gone? So this is supposed to be dealing with the offset. All it's really doing is flattening the whole thing completely. Well, I don't know. I mean, sorry, you didn't really see that, did you? Let's put that in there. So, this thing that I've put in, which is supposed to be just adjusting it around the center point a bit, doesn't seem to be doing that. It seems to be, I mean, it is moving it up and down, but at the same time, it's changing the output. I had a much larger output, and I can twist this to get back to something approaching that, but then it's now offset. So I can put it back to somewhere in the middle, which is there, but then I lose the level of output. I don't really understand. I don't understand what I'm trying to do. But there's this last bit that says boosting the output signal. So let's finish off with this last bit. It says to fix this. So something evidently has gone awry. Did I not read that? Oh, it says if you turn the gain all the way up, you still see the maximum voltage swing is pretty far from 10 to 10. Yeah. We already got that. So we need a boost at the end. To fix this, we can simply use a bit of our subtract op amps gain, because right now we are really only using it to subtract our two signals, not to amplify the result. We can change that by making the output work harder to equalize the two input voltages. In order to make it work harder, we have to change relations between the resistors around the op amp. If we make two left-hand ones smaller than the ones on the right, we're essentially creating two effects that synergize. First, the voltage swing at the non-inverting input will get bigger. Okay, so what we're doing is we're changing the values around the op amp to make it work harder to create more voltage. Alright, so this is the last push then. So with the resistor values that he's chosen, we'll get a 10 volt peak to peak output for a 10 volt CV input. In order to do that, we'll have to add a CV input and a signal output socket. Also, we'll keep the manual CV control in the circuit so we can dial in an offset value. Okay. And with that, our VCA is done. So we've got this last little bit. I'm actually going to zoom in this time. So maybe this is working and I've just got a crap output. So what we're going to do is going to put in a couple more sockets. So let's just see if we can finish this off now that we've hit 3 hours on this video, which I think is plenty. Don't you? I think so. So let's just try to push through, get this last bit done. possibly. It just depends how much change there is involved, because actually there's probably quite a bit. Yeah. Yeah. No, okay, I think that's probably enough. I think that's probably enough. Because there's quite a few changes we're going to have to do on this. So I think what we'll do is when we come back, we'll come back tomorrow to do the soldering. Go back to my first camera. Okay. So yeah, I think that's too long now. That's long enough. I don't think I can successfully do any more without losing my mind. It's been challenging and difficult trying to understand some concepts of how it works. You know, I'm not in any way trying to say it's easy. I'm not also trying to say it's impossible. It's totally graspable. And the process that we're going through, I mean, the emulations, the circuit emulations are brilliant. They really are helpful. But you've still got to grasp this information and somehow square it away in your head, which is a challenge, definitely a challenge. But I think I understand the differential transistor bit. I think I understand the pulling away of voltage, which creates a negative feedback, which creates the which places you on the straightest line possible to give you a linear response. I think I get that. And I get this offset if it would work as we'd expect it to. So yeah, I'm seeing how all the different parts are coming together, essentially. Now what we're required to do is put in a couple more patch sockets so that we actually have an input, an output, and a CV control over it. Now that's just a matter of replumbing this breadboard, and I think I'm out of energy and I'm not going to be able to do that right now. But what I will do is I'll do it tomorrow during the day, just so that I have this finished and set up so I can show you that before we then solder it together. Does that sound like a plan? Yeah, Ken, exactly. That's enough. That's enough. So tomorrow evening, same time. It won't be as long as this because we're just soldering together a simple module. It will be no problem. But we'll start off with this finished. I'll come back tomorrow and just finish that bit off. And we'll have a quick look at that. And then we'll solder the thing and the job's a good one. So yeah, hard. This is a fascinating series. And I think I'm aptly demonstrating that it's not simple. It's not child's play. It's meaty and interesting and requires thought and a methodical approach. But the content of the manual is excellent. The examples are great. Fiddling around with oscilloscopes is a learning experience, and that's what this is all about. So, flippin' heck, are we putting the work in, boys and girls? We certainly are. Great, thanks Philip for that. Complicated bit is a compensation for the faults. Yeah, it's almost as if you keep doing something and that makes something else worse, and then you've got to work out a way to how to stop that from doing that, and then you then try to improve something else, and then something else and something else. Oh, Andrew, always on the ball. Yeah, cool. Right, so that'll do. I'll stop wittering on now. Excellent. Thanks for joining me. Do all those things like subscribe and stuff. We're going to be doing this with every module that comes out. And there's 9 modules. This is module number 2, so we've got a lot more learning to come. So I don't know what's going to happen next. But tomorrow night, 7:30, we'll join back again, solder the thing together, and I'll run like LFOs and envelopes through it and stuff and see what happens. That sounds like a good idea. So thanks for being with me and all that. I'll try to find my output thing. And I hope in some way that was useful to somebody. All right. See you later.